Okay, right, so good afternoon everyone, and it's awesome to have our first webinar for 2021. And it's really fantastic to see so many people here and that you're joining us today. So welcome, and especially to our presenter Jennifer, and I'll leave that up to Pam to tell you a bit about her just now. Right, so some suggestions for happy webinars for those who have not joined us before. It would be better if we kept our cameras off and our sound off, just so that everyone can join in equally, and it makes the streaming a little bit better. So please just do that. And then we also ask that you do put all your questions in the chat, please. The chat is on your screen at the bottom. If you could just please put a question in the chat, we keep that, refer back to it later, and make sure we've answered all the questions that you might have. Okay, and then please, if you're not a member of SAGTA, it would be awesome if you do join us. You do get quite a lot of fantastic support, and our aim is to really grow it and make it, it is already, but make it even bigger, the biggest subject related association in South Africa. Right, so that's fantastic. We are looking at weather stuff today, and I just thought that picture of the cats or categories is just the best. Okay, right. And then for SAGTA members, if you are a SAGTA member, won't you just pop in the chat quickly, just go yes, 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 so we know how many SAGTA members are actually joining us today. It also helps us just to keep some records of how many people we are actually getting hold of. So just put yes in the chat so we know how many SAGTA members are joining us today out of everyone. The recording will be made available, yes. So if you're a SAGTA member, you will have access to that. Amanda will email the link later. And then additional resources from Jennifer, which is awesome, is also going to be made available with that same email. So please look out for that. And thank you, Jennifer, for those. It's just fantastic. Okay. Right, so what we'll do today is, I'm just going to do that one quickly. Right, we'd like to give Clinton a minute, and then we're going to continue with Jennifer's presentation. And Pam is kind enough to do a little quiz for us at the end. And this book over here, which is just fantastic, is the prize which is up for grabs. So you'd be encouraged to take part and see if you can actually answer the questions on climate and weather, which Pam has set for us. Okay, we'll give you that link a little bit later. So, Clinton, up to you.
Okay, good afternoon, everyone. Can you hear me, Inika?
Yes, thank you.
Hi, yes. I just wanted to quickly take this opportunity to tell you about the South African National Geography Olympiad this year. It's going to take place on Monday, the 18th of May, and it's a 2-hour multiple choice question online Olympiad, which the learners will be able to do from 7 in the morning until 5 p.m. that afternoon. They do need to have a laptop or smartphone or iPad or tablet, some smart device, and then it's 60 Rand for the school to participate. And however many students you have, they each pay 40 Rand each towards the Olympiad. The school collects the money and then makes one deposit. For more information there, you can visit our website. You can see it there, the last bullet. It'll tell you more information and also how to go about expressing an interest to participate in this year's exciting competition. So we look forward to see as many of you there as possible, and we're hoping to have more schools than last year. Thanks.
Thank you so much, Clinton. Right, Pam, it's up to you. Okay, it's muted. Okay, I think then we're just going to ask Jennifer to please continue. Thank you, Jennifer.
Thanks, Inika. And hi, everyone. I'll just share my screen quickly. So for those of you, oh, I'm starting on the wrong slide here. Here we go. For those of you who haven't encountered me before, My name is Jennifer Fitchett. I'm an Associate Professor of Physical Geography at Wits University. And my primary field of research is in a subdiscipline of climate science called biometeorology. So we explore the impacts of climate change on plants, animals, and human communities. And I'm currently representing the African continent on the International Society of Biometeorology. And closer to home, I'm the president-elect of the Society of South African Geographers. So weather certainly is something I'm very passionate about, but as is geography, and it's always a great honor and pleasure to engage with the members of the South African geography teachers, formal and informal associations. And every year I give a talk to at least some group of people involved in geography teaching. So this particular talk, Inika very kindly titled for me, All Things Weather That Confuse You. And hopefully I'll be covering some of the major climatic events of recent weeks and months in South Africa, but also covering some of the broader issues around climate science and how we come to understand that. My background, and there are a couple of slides here which will be very technical, and I don't expect you all to engage with them, but my background at undergraduate level was a double major in ocean and atmospheric science and geography and environmental science. And I then went on to specialize in paleoclimate for my PhD. So what I want to start off by stressing is this particular slide. Are you confused about the weather? Are you unreasonably confused about the weather? And what is driving your confusion and or lack of confidence in teaching climatology? Because I very strongly believe that actually the third of these is probably the most relevant for all of you. If I think back to when I was in high school, and it is feeling increasingly far behind me, certainly if I think across all my years of study, the best climate education I got was in high school. And nothing that I did at university, whether in South Africa or in London, ever surpassed the grounding in climate science that I got in high school geography and from my high school geography teacher. So I think that some of the biggest challenges are that as a cohort of people who are involved in education, and I include myself in this, it's far more an issue of imposter syndrome than it is that we are actually genuinely confused or that we are unreasonably confused. So instead, what I'd like to suggest is that the confusion or lack of confidence in teaching climatology is not as a result of your own knowledge, that none of you are laymen when it comes to climate or geography. You're all experts in geography teaching, but rather that what's leading to any degree of confusion or lack of confidence is rather, first of all, the fact that we're living in an age of climate variability and change. We've had a 1 degree increase in global temperatures over the past century. We're projected to experience increases in Southern Africa of 4 to 6 degrees by the end of the century. And in that context, a lot of what we know is in an environment that is changing very rapidly. And so those very variables are changing in and of themselves. We're also living in an age of tremendous scientific advance. I remember when I was at school, I always thought that I was born too late, by many, many centuries too late, that all of the big inventions and all of the big discoveries had already happened. Newton had the apple fall on his head, and now we know everything there is to know. And of course, that isn't the case. I think this past year and the tremendous development that's taken place in terms of understanding and treating COVID-19 really speaks to how quickly science is advancing. And so some of the confusion or some of the lack of confidence comes because of the fact that what we learned 10 years ago might not be true today, because we've understood things better and we've understood systems better. Linked to that is an information explosion. We have more access to information now than we ever did before, and that information comes from a huge variety of sources. So whereas in the past we would have some sort of key textbooks on a topic, and there'd be a lot of debate and deliberation over which the most appropriate textbooks are, today both us as educators, but also all of our students and all of their parents are getting information from a huge variety of sources, many of which are spread via social media, and many of which are from a range of different authorities, some of whom might be experts in the field, but many of whom might just be people who have a keen hobby for the climate or environment, or people who are spreading information that they've heard that was interesting to them without determining the veracity of those sources. And then linked to that, of course, is the increasing issue of fake news. One of my honors students last year who got the top project prize did a study on Cyclone Idai and the extent of fake news regarding media reporting. In an analysis of 84 media articles, he found that over 70 of these had at least one piece of information that was found to be incorrect or inaccurate when compared to official meteorological sources. So if 7 out of 8 news reports that we're reading are deemed to be fake news, and those are often accidentally fake news, if we think about the fact that there is a deliberate spreading of fake news around climate variability and change, and as a result, climate system science, we really have to then be careful about what kind of information we're taking in, our students are taking in, and their parents are taking in. And it does break down our own confidence when we're teaching a topic and we're presented with information and it's difficult to determine how true that information is. So I want to begin this talk by saying that you are not confused, that there is this wealth of confusing information, and that you're certainly not doing a bad job in teaching climatology. And I feel quite confident in saying that because I'm the first person that our first year students at WITS in geography encounter. I teach approximately 250 of them every year. And I can tell you that these students are coming into university very well prepared in terms of their climate knowledge and in terms of their geography knowledge. So I don't believe that you are confused. But what I do hope to do is to cover a couple of issues around contemporary weather phenomena over recent weeks and some of the broad climate systems that we've experienced in Southern Africa over recent decades. Part of what I'll be presenting to you is from a book chapter that I wrote last year towards a book that is being submitted to the publishers in September of this year. It's a book on tourism and climate change, so a little bit off the primary topic here, but one of my contributing chapters is on the climate of South Africa. So I'll be presenting some images from that book. Those won't be included in the SAGTA pack that I've created because, of course, the book is forthcoming. But when the book has been published, I will also give you the details of that. So let's start off with what caused the rainfall over the past 2 days. And this is a UMET-STAT image shared by AfriWX yesterday. And to those of you who are familiar with reading off climate from remote sensing, you might have a clear idea here. But it's a phenomena that is not very regularly discussed in the high school syllabus. And indeed, it's something that, although it was part of the original work of, for example, Tyson and Preston White in the Weather and Climate of South Africa, it's something that hasn't been very widely discussed until the past decade. So what we're looking at here is a distinct cloud band that extends from the northeast through to the southwest. And it's termed a tropical temperate trough. So it's connecting the low pressure that's situated at the moment, southern Botswana. It can extend all the way up into Angola as the Angolan low, and it extends down towards the high pressure located just off the southeast coast of South Africa. And we're going to talk a lot more about these tropical temperate troughs because they are a very interesting feature that particularly Chris Reason's group at UCT has done a huge amount of research on in recent decades and has a very important role in the summer rainfall that we experience in the interior of South Africa. So that's what's caused the rainfall over the past 2 days. And if we look at a synoptic map here, we can clearly see that low pressure situated over sort of Namibia, Botswana, and the high pressure located just on our east coast of South Africa around sort of Durban through to Port Shepstone. The second question is, did Tropical Cyclone Guam make landfall? And here I've got an image from NASA of the cyclone, very distinct eye, visible at this point in time, and huge swathes of cloud bands over Mozambique. Now, at this point in time, and when it was classified as a tropical cyclone, it didn't officially make landfall. So although there is a huge influence of the storm over land, and we can see that from the cloud bands and certainly the rainfall that was experienced from this in Mozambique, as well as a degree of rainfall along Swaziland and northern KZN, a storm is only officially termed to have made landfall when the eye moves over land, and that didn't occur at this point in time. However, it would be inaccurate to say it didn't make landfall at all, because if we look at the history of Cyclone Guam, we see that before it was officially categorized as a Category 1 tropical cyclone, at that point it becomes a yellow dot. When it was a tropical depression and later tropical storm, it did actually make landfall and then move back off the coast and into the ocean. So again, there's been a lot of incorrect media reporting here, either that it did not make landfall at all, or that there was no influence of Cyclone Guam on Southern Africa. Both of those are incorrect, but it requires a lot more nuance to understand what exactly we mean by landfall of a storm versus influence of a storm, and at what point are we concerned about landfall. We certainly are concerned when it's making landfall, even as a tropical depression. They are still significant sources of moisture, and that moisture is deposited very quickly over a short period of time. And then the last question is, was Tropical Cyclone Eloise responsible for rainfall in South Africa? And I certainly have read a huge amount of commentary on this, particularly on social media, arguing that Cyclone Eloise had no impact on the rainfall that we experience in South Africa, and that was constrained only to Mozambique. And so here we've got some of our Terra Modis images that have been shared by Zoom Earth. What we can see as the bands striped off here, of course, is the movement of the satellite across the Earth. And overlaid on that is the storm path. And so we can see this is on the 21st of January in the morning. We can see that the storm is located in the Mozambique Channel. It then moved closer to Mozambique and started to form very distinct cyclonic cloud bands. And then by the 23rd of January, we've got the storm having made landfall. And you can very clearly see that within that cyclonic system, the cloud bands have covered a large area of Southern Africa, including Limpopo and Mpumalanga. And we've got some small cloud bands that are just moving into Northwest Province at that point in time. And by the 24th of January, if you're following the storm track path over here, we can see that there is still a distinct storm and that's covering a large area, including Johannesburg. By the 25th of January, I've just moved the satellite image a bit further up so that we can clearly see the rest of the country. You can still see where the edge of these cloud bands is, and you can see why they're plotting the storm path where they have, and that's with the input of the Meteo France and the NOAA IB tracks, that we've still got a distinct cyclonic system, and we've got the impact then of those cloud bands right the way across Johannesburg and through into Northwest and extending into Botswana. So any reports that say that Eloise had no impact on rainfall in South Africa are incorrect. And we need to understand that, of course, it was moving through in a very complex system. And it was followed very soon after by the impact of a mid-latitude cyclone. And we're starting to see here a tropical temperate trough pattern where the tropical cyclone itself is forming that low pressure anchored in Botswana and Namibia that would then lead down to a tropical temperate trough that extends to our high pressure systems. So a very complex system, and it's not surprising that people were confused, but certainly would be incorrect to say that there was no impact of rainfall over South Africa. And this is probably what started the idea for this webinar, was that in reading all of this material, I'd started to doubt myself and the many years of work I've done on tropical cyclones. And so in consulting with Professor Francois Engelbrecht, who's our distinguished professor of climatology, his response was quite blunt in this regard, confirming that indeed there was direct impact of the storm on rainfall, and that was appearing both in the satellite images I'm showing you, but also in reanalysis data. So with that background over a couple of recent events, I want to present a quick overview of the climate of South Africa. So this is from our forthcoming book that will be submitted to Routledge in September. An image that I've produced for that, explaining the various components that I cover in that chapter. So we've got our tropical temperate trough that I've discussed, and I'll go into more detail. We've got the two semi-stationary high pressure cells, the South Indian high pressure, also termed the Mascarene high, and the South Atlantic high pressure, also termed the St. Helena high. We have quite frequent coastal lows in summertime that can extend anywhere from Cape Town through to about Durban. We know that we have the development of tropical cyclones with the warmer tropical waters. We've got an ITCZ that's located quite a bit further south than usual, although remaining north of South Africa and cutting across central Madagascar and central Mozambique. We have the Angolan low, which anchors the tropical temperate trough, and extending down from the ITCZ and through the Angola low is the Congo air boundary. And again, something that's fallen out of vogue in terms of our understanding of the Southern African climate systems, but something that Tyson and Preston White discuss in a lot of detail and is coming back into the academic literature. We then do have mid-latitude cyclones during summer, of course, but they are situated too far south of the country and they very seldom pass through the country, but occasionally with particularly strong westerly wave perturbations, they may do so. If we move through into winter, we've now got the northward displacement of the ITCZ, the Congo air boundary, the Angolan low just about disappears. Our Mascarene high and St. Helena high, or South Indian and South Atlantic high pressures, have moved a bit further north, and they tend to occupy a greater area over the two oceans. We also have a transient high pressure that appears over the subcontinent during winter. This is what historically has been termed the Kalahari high pressure. The name suggests it is semi-stationary, which it is not, so we would rather term that as either semi-permanent or a transient high pressure. And often those high pressures form high pressure ridges, which then result in cutoff lows that are again occurring anywhere between Cape Town and Durban, breaking off low pressure trough, many of which are formed by the mid-latitude cyclones, which are now located slightly further north and move across the country. So a very quick overview of the major climate systems. What those then create is what can be plotted as a Köppen-Geiger map, a number of climatic zones across the country, which then each host very different biomes. So the benefit of the Köppen-Geiger map as a system for classifying the climate is that it incorporates both seasonal differences, so the difference between our summer rainfall zone, winter rainfall zone, and year-round rainfall zone, as well as temperature differences, whether it's particularly cold, temperate, or hotter, more tropical conditions, and then the amount of total moisture. So are we talking about a very moist region, such as a tropical monsoon, or are we talking about a very arid desert type of region? And it's one of the few systems that incorporates all three components of climate variability, and is a therefore quite sensible way of mapping out the differences in our climate across the region. So one of the big vision is when the seasonal brackets are, and until last year, there was no consensus on this. So what I'm showing to you now is a paper that was published last year by my very recent PhD graduate, Dr. Adriaan van der Walt, where he performs the first statistical classification of South Africa's seasonal divisions on the basis of daily temperature. And on the right-hand side, we've got the output for that. So unfortunately, it doesn't show up too well on Zoom, but we've got a number of different cities in a number of different provinces. And although there is consensus for all cities that summer spans December, January, and February, for most cities, March is also included in summer. If we go into winter, June and July are winter for any city in the country, but in August, only about half of the cities are classified as winter. A couple of cities are classified as winter right the way through into November. Our spring months, there is no uniformity in terms of when spring is, and our autumn months, there's no uniformity about when autumn is. And this is very significant because a lot of our confusion about the weather is because we would like our weather to fit into our astronomical boundaries, i.e. pinning them to the equinoxes and the solstices. But that doesn't follow that clearly. So of course, around end of June, beginning of July, and end of December, beginning of January, we do have a uniform classification of summer and winter. But when it comes to our spring and autumn, those aren't tied to the equinoxes. This is due to a number of features, including many of these transient weather phenomena. So the fact that we've got mid-latitude cyclones that are transient, tropical temperate troughs, a transient high pressure over the interior in winter, means that we have considerable spatial heterogeneity in the expression of our seasons. A similar thing has been found if we look at rainfall seasonality. So this is another of my former PhD graduates, Dr. Sarah Rofe. She looked at classifying and mapping rainfall seasonality in South Africa and found that across 59 published maps that have been produced since 1938, there is tremendous inconsistency and confusion. And this is confusion amongst academics publishing peer-reviewed papers. So the best we can get is a 75% consensus of where the summer rainfall zone is, which is the dark terracotta red. The best we can get is a 75% consensus over where the winter rainfall zone is, and that's the dark blue, and a 75% consensus over the year-round rainfall zone, which is starting just east of Mossel Bay. The rest of the region, there's about a 50% agreement, or there's just confusion about which zone we're in. So again, the confusion that you may be feeling is confusion that everyone's feeling. And part of a reason for both of these is because our seasons are changing. So it's not just that everyone's approaching this with a different method, which is true too, but that we have a problem that in the period of the last few decades, our seasons are changing. So this is another of Sarah's papers looking at changes in rainfall seasonality across South Africa from 1987 to 2016. And over here, she's using a seasonality score, and it looks at when we have both hot and rainy or cold and rainy conditions. And we've got our winter rainfall zone down in the southwestern tip, that bright blue area, and we've got a distinct summer rainfall zone from orange through to red. But within that, we've got a lot of change happening. So every time you see a large triangle, we're talking about a large change. And if that triangle is colored in, it means that it's a statistically significant change. And we're seeing that there are changes both to more pronounced seasonality, which will be your positive arrows, upward arrows, and a reduction in seasonality, i.e. distributing rain across the year, which is our downward arrows. So again, we're in a system where the climate is changing faster than we can even understand the climate. And so in the process of trying to determine consensus over where our seasonal brackets are, those seasonal brackets themselves are changing. So the second thing I want to talk to you about is the tropical temperate trough, and I've given you two very broad and quite vague, I think, introductions to those. So I'm showing you another satellite image here, again showing a tropical temperate trough. This was from, I think, the 30th of October last year, or certainly that's when Francois Engelbrecht and I were sending these pictures to each other. Very, very distinct cloud band extending from Namibia right the way down and past Durban and Port Elizabeth. So this is one of many papers that has come out of both France, where they have a particular interest in our tropical temperate troughs, as well as a large amount of work that's coming out of UCT recently. During our summer months, approximately 30 to 60% of the rain that we experience in the summer rainfall zone is caused by the tropical temperate trough. So this is a low pressure trough spanning the easterly and westerly waves. It's characterized by this intermittent northwest to southeast cloud band extending from northeast Namibia to about the south coast of South Africa. And the strength and frequency of the tropical temperate trough is influenced by the sea surface temperatures over the Indian and Atlantic Oceans. And because of that, there's a very significant impact from the El Nino Southern Oscillation, the Benguela Nino, which is a transient influence over the west coast of Southern Africa, and the Southern Annular Mode. The South Indian Convergence Zone is the preferred region of formation. So quite separate to the Intertropical Convergence Zone, we have a South Indian Convergence Zone, and there are a number of these along the eastern coasts of each of the major continents. And this is the preferred region of formation and why we have that distinct pattern that forms. There are approximately 15 tropical temperate troughs per year, or 150 per decade. Now, this particular cloud band is often confused either with what I often hear is a interference between a tropical and a mid-latitude system, but people, which is not incorrect because we are talking about something that spans these two systems, but the argument that they are colliding with one another would be incorrect, or that they're interpreted to be the ITCZ itself. So when people see these slanting cloud bands from Namibia through to the southern regions of our KZN coastline, it's often interpreted to be the intertropical convergence zone, but of course it doesn't actually extend that far south in southern Africa. So what you're looking at there is the tropical temperate troughs, and they experience weather such as what we've had yesterday and then today, and what's going to continue over the week. One of the key features that you'd notice, if any of you have friends in Mafeking, and I have a very good friend working at the University of Northwest Mafeking, they started to experience rain about a day before we did in Johannesburg. And so you'd see these systems sort of moving through as they extend from being a low pressure system through to a low pressure trough. And as I said to you earlier, they are quite distinct on synoptic maps, although they aren't drawn in always as a trough when they begin. So over here, we've got our low pressure cell at 1012 hectopascals. And then you can see that our high pressure has had to move around the edge of a system. And that's a key diagnostic that we've got a trough that's formed over there. The existence of the high pressure critical to the tropical temperate trough because it's forming a trough that leads to that high pressure in connecting us with our subtropical high. And then the third thing I want to speak to you about is what is happening to our tropical cyclones. And this is an area that I've done a lot of research in, dating back to 2011 when I started doing work on tropical cyclones. And every time I think I'm moving away from it, something else really exciting happens. And of course, we've now just had a very exciting tropical cyclone year. We've had 3 tropical cyclones that have been of interest to Mozambique. That's quite unusual. We normally experience about 1 every couple of years in Mozambique. And increasingly, tropical cyclones are becoming something that we in Southern Africa are paying a lot of attention to, and that we need to start thinking very carefully about in terms of adaptation. So the first thing that I want to talk to you about is the pattern that we've seen over here with Cyclone Guam. So as we said, it didn't officially make landfall when it was a cyclone, but something else that's been of interest to many people is the fact that it moved in the wrong direction. So instead of going from east to west, as we expect them to, it's largely in its lifetime gone from west to east. And so one of the misconceptions around this is that it's because it's moved too far south that it is then carried across by the westerlies. And if you Google why do tropical cyclones change direction, Encyclopedia Britannica lists that as the first reason. And that's not actually correct. There is an influence of the easterlies and westerlies, but that's not the primary reason. So this is not uncommon, the storm moving from west to east. Indeed, the vast number of tropical cyclones, if they exist long enough without dissipating, will retroflect. So they'll begin by moving from east to west, and then at some point in time, as they start moving further and further across, they are also moving towards the poles, and that's because of Coriolis, and Coriolis continues to act and they end up retroflecting. So the very short answer is that the pattern you're seeing on the screen in front of you, and we're looking at every single tropical cyclone that has ever formed, and this is courtesy of NOAA's IB tracks. I think this particular image is a couple of years outdated. It's very common that we would see them retroflect because of the action of Coriolis. So we know we are deflecting to the left. The further we move, the more we're going to deflect left. It is going to retroflect on itself, and it's going to do so more and more of a pronounced manner as we move closer to the poles, because we are now having an enhanced Coriolis effect. Coriolis is a feature of latitude. And that is because the world has a larger distance to cover at the equator as it would at the poles. So to go right the way around the world at the equator is a further distance than going right the way around the world at the poles. And if you wanted to do that at the same in the same time, you'd be doing it much faster at the equator than at the poles, and vice versa. You'd be traversing a much larger, shorter distance in the same time if you were at the poles, which it changes your velocity. So, as I said, Britannica tells you that they recurve or retroflect because they're carried by the easterlies and then by the westerlies, and that's not correct. What is correct, and I'm going to click through this quickly because I don't want to overwhelm you with physical oceanography, but what is correct is that we have angular momentum, which then induces torque, which then induces forced precession. So our tropical cyclones have an angular momentum with respect to the Earth's axis. So they are moving on something that is moving underneath them, but they also have an angular momentum in and of themselves because they are a cyclonic system. The angular momentum has to be preserved, and as they move polewards, the distance to the axis reduces, which creates an eastward acceleration. And eventually over time, the eastward acceleration from the fact that we are moving over something that is spinning underneath us with a particular velocity and acceleration would exceed the westward movement and the speed of westward movement of the system. And that then means that they will retroflect and start moving towards the east. And in this process, the trade winds and the westerlies will create friction, which will either oppose or enhance this effect, depending on where you are. So for those of you who don't trust me, here are all of the equations. So I'm not going to go through them. I'm not going to overwhelm you with them. But what this is demonstrating, first of all, is the movement within a particular latitude and the force that is applied to it for it to do so. What is important to recognize is that normally a hurricane or tropical cyclone does not follow the Earth's rotation exactly. And so the effective rotation rate is somewhat different from that of the Earth. It's dodging a number of existing and semi-stationary high pressure and low pressure systems, as well as landforms as it does so. As I mentioned, there are two angular momenta associated with the hurricane, one with the spin of the hurricane and one with the hurricane moving on the Earth's axis. And as it starts to move to the poles or in either direction, it's then going to have a distance to the axis, which is decreasing. Because we need to conserve angular momentum, the velocity must increase. And that then is going to create a system where we end up with a reduction that is to the magnitude that it would change in its net output. And so just to give you an idea here, if we're looking at the easterly velocity at any point of latitude, we're starting to see a reduction as you go up towards the poles. So short answer here, and thank you to San Jose State University for this. If we consider a tropical cyclone at latitude 20 degrees south, moving west at 24 kilometers an hour, the speed of the storm's movement is 6.7 meters per second. However, due to the Earth's rotation, the absolute velocity would be the 435 meters per second of the Earth's rotation minus the 6.7, which would give you 4.28. So if it moves to a higher latitude, its distance from the axis of the Earth's rotation is smaller, and to preserve that angular momentum, the easterly velocity must increase. So as it moves south, eventually it's going to that 6.7 is going to become so irrelevant that it's going to shift from having a westward to an eastward movement. And I give another more detailed answer here, where we're talking about the reduction of 3.75% as we move from 20 to 25, which then changes the rate of the net velocity and changes us from east to west. So I did promise I wasn't going to go into too much detail here, but it is important, I think, again, in an era of fake news, to be able to show these equations and show how we work that out. A couple of other changes that are happening in terms of tropical cyclones. This is a paper of mine from 2018. We are now experiencing Category 5 tropical cyclones in the South Indian Ocean. So the first of these was in 1994 with Tropical Cyclone Geralda. And over time, we're experiencing an acceleration in the number of Category 5 tropical cyclones. None of these have made landfall on Mozambique yet, thank goodness, and long may that last. But many of these are forming in the South Indian Ocean and affecting Madagascar, the Seychelles, or dissipating before having a major impact on land. As this is partly as a result of the sea surface temperature increases, but also as a result of the fact that we are seeing an increase in vertical shear. So we're having less storms forming because they're being broken up by vertical shear, but those that do form are then able to increase in their intensity. So that's a major change that we are seeing, and Cyclone Idai as a category on the border of 3 and 4 storm is starting to give us an idea of what these storms might look like going forward. We're also seeing that we are experiencing tropical cyclones further and further south or polewards than we were before. So this is work of one of my former master's students, Michael Pillay, looking at the incidence of tropical cyclones south of the Tropic of Capricorn. So originally we'd say that they form between about 5 and 20 degrees. There are, as you can see on the screen in front of you, quite a number of tropical cyclones outside of that region. And again, those storms are increasing in their intensity over time. So as the ocean gets warmer and warmer, and the colored bands that you're seeing here are the sea surface temperature isotherms, we are getting an increase in the number of storms that are occurring further and further south. This, of course, is of concern to us in Southern Africa because tropical cyclones such as Eloise are likely to become more frequent in their occurrence. And then this is a big topic of debate at the moment. There was a research letter that was published and then later corrected in 2018 by James Cosson, who's one of the top tropical cyclone experts, arguing that there has been a global slowdown of tropical cyclone translation speed, i.e. how quickly it's moving across an area. And that's been followed last year by a piece by Kelvin Chan, another person who's been involved in a lot of tropical cyclone work, arguing that this is not the case, that there is no evidence, particularly when you try and model these storms, to demonstrate that this is true. So this is something that needs a lot more work, and particularly it needs to be explored where we do have geostationary satellites, where we can keep an eye on a storm from one single perspective throughout its lifespan, and to be able to determine what proportion of these storms are actually moving. And if we cannot then replicate that in modeling, why that's the case. Why are we unable to then model what is occurring in nature? What variables are we not considering? If it is the case, it's significant because a slower moving storm would then spend greater time over the ocean, and particularly greater time over warm chord eddies in areas such as the Mozambique Channel, which would allow them to intensify even further. It would also speak to one of the most interesting patterns that we've seen with Cyclone Idai, and in the same year, 2 other cyclones, which all showed that same pattern in the Indian Ocean of slowing down before they made landfall. So a big debate at the moment. There is no consensus on this, and it's something that does need further research. So again, we're going to be in the position where the stories that we are able to tell are changing because we're learning more and more about these systems. So that brings me to the end of what I prepared to share with you today, but I'm very happy to take any questions at this point.
Thanks, Jennifer. There were some questions in the chat while you were speaking. Paula asked about line thunderstorms, and it referred to that summer image. Paula, is that right?
I'll just stop sharing for now so that I can see the chat. Okay, I see the question now. Is it the same as a line thunderstorm? Not entirely, but they're not mutually exclusive. So we can have line thunderstorms that form part of tropical temperate troughs. Often what we classify as a line thunderstorm is a much shorter lived system. So a line thunderstorm would tend to form and dissipate within a couple of hours. We also get them in the middle of our summer, and they also follow a similar pattern in that they tend to form in the northwest and move through towards Mpumalanga, but they can do the opposite. Those are storms that build on themselves. So a storm cell will build, and that will feed the next storm cell, which will feed the next storm cell, and so on and so forth, which can happen at the beginning of the development of a tropical temperate trough. But these tropical temperate troughs tend to stick around for a couple of days, which is the forecast that we're seeing here, although there is sun streaming in the window behind me right now. So yeah, I think that answers that question, but if anyone wants greater clarity, please let me know.
Llewellyn asked if that's a heat low.
So the Angolan low is thermally driven, but it is a semi-stationary low. So we experience an Angola low at some region around Angola, Namibia, Botswana, just about the whole way through summer. It's just stronger, weaker at particular points in time. So it is a convective low, but it is a bit more stationary than we'd expect a normal short-lived transient heat low to be.
Any other questions? Anyone? No one. While we wait to see if there are any more. Oh, there's a question for you, Jennifer.
Okay. Towards the end of 2020, the world experienced La Nina. Has it had any effect on the intense weather conditions in the US? And has it intensified this year's tropical cyclones anyway? So I think the second half of this relates to tropical cyclones in Southern Africa. We have an interesting relationship with El Nino, La Nina. It's far more important in terms of how our storms move than the number of storms that we experience. And so the type of retroflexion that we saw with Guam is quite typical of either a positive or negative El Nino event or an ENSO event. It is a much shorter La Nina than we'd normally experience. So I haven't looked at our MEI values recently, but it is quite short-lived. What we also need to consider is that the conditions globally have been altered to a very small extent by lockdown conditions. So one, we have had a change in the amount of air pollution, and two, we've had a change in our amount of city heating because of behavior in the cities. And so that is complicating the appearance of what we're seeing. But in terms of at local level, we are definitely seeing much wetter conditions than we normally would, and that is quite typical of La Nina events. How common is it for tropical cyclones to form in the Mozambique Channel? I have the answer to that in work I did a very long time ago, and I wonder if I can pick it up. I can tell you an exact number if I can find a figure I produced a long time ago. Not nearly as common as the tropical cyclones that are forming in the South Indian Ocean, as a short question. But they can form there, and they will form there, particularly in conditions where you've got a large number of warm chord eddies, and therefore much warmer sea surface temperatures in the Mozambique Channel than in the main ocean, which is always the case. And in particular, we will see them if we have these slower moving storms, because those are the type that would then be able to develop into a full tropical cyclone. But I am trying very quickly to find this figure that I produced, and I will share it on the screen. 34.5% of the tropical cyclones that make landfall in Mozambique form in the channel. So I will just share that figure for you. So this here, trying to move all my Zoom windows out the way. Here we go. This is 34% here, 34.5% that form in the Mozambique Channel and make landfall in Mozambique. The rest of those that make landfall in Mozambique are 13.5% that track south of Madagascar, and those are the ones that are forming and existing south of the Tropic of Capricorn. 5% managed to make it across Madagascar and keep going towards Mozambique, which was the case with Eloise. And then we've got 28.8% that form sort of near the Seychelles and move towards northern Mozambique and just into the channel at the end. Okay, eddies in this context. So here, if I'm talking about warm chord eddies, I'm talking in an oceanographic context. So I'm talking about filaments that break off the Agulhas current and move their way down through the Mozambique Channel. So I know that in old textbooks in particular, there's a Mozambique current that's drawn in. That's not an official term. So it's part of the Agulhas current, but to move through the channel, it sort of separates and the main Agulhas current continues to move past Madagascar. We get filaments that break off, and those then spiral, and so they form these very contained pools of warm water, which we call warm chord eddies. You also get similar effect when we have the breaking off of the Benguela current as we have the retroflexion of the Agulhas. It's warm pools or cold pools of water that break away from a major water mass, which is a current, and then move through the ocean. They're usually not very deep, but they do increase the temperature locally. Okay, what approach do we take when teaching tropical cyclone information? Textbooks and examiners expect answers which are not entirely accurate, but if we teach otherwise, learners will be penalized. I agree. That is a huge problem. And I think the best way of doing it is you are preparing students for matric exams in particular. And as you say, those are exams that are set with particular questions and with particular answers in mind, and they're often set with those textbooks in mind. So I'd say two things. I'd say, first of all, that's the amazing thing about having an association such as SAGTA, which is that I think that with enough numbers and enough strength, you'd be able to start pushing for change, and particularly where there are common misconceptions, to be able to change those and get those rectified so that the textbooks are corrected and so that the exams are looking for the correct answers. The second thing is, and as an educator, I don't like to say this, but I do think that there is an extent to which you have to be pragmatic, and you have to say to students, this is, when you read a question like this is the type of answer that it is looking for, which is terrible, rote teaching, I know. But then to have perhaps a day or so where it's a research day, and that you then present the fact that research is changing, and why research is changing, why we've got new scientific discoveries, what the impact of climate change is, and give them a day or two to really have an exposure to the broader picture, but then bring them back to, okay, but this is the question you're going to be asked, and this is the answer that you're going to need to give. I know that a couple of years ago, I was involved in a day at the American School of Johannesburg, where they had a research day on paleoclimate research, and that was very much the case. So they're not going to be asked questions on paleoclimates, but it allowed me to do this really nice deep dive with them in terms of how we use tree rings to reconstruct past temperatures from carbon and oxygen isotopes, and how that differs from ice cores and all sorts of things like that, which allows them to understand that there is no singular answer, that science is rapidly changing, but at the end of the day that there is a curriculum and they need to answer all of that from the curriculum. So I think that would be a lovely idea, and certainly if that's something that you do want to get off the ground, I'd be very happy to help any of you with that, because certainly when we get to university, we then say to people, we say to our students in the first block of first year, we are not allocating you any textbooks, we're only going to give you peer-reviewed articles, they're only from the past 5 years, and the reason for that is because information is changing so quickly, but also that peer-reviewed articles are more likely to be more accurate. But again, there are disagreements among those, as in the last example I showed you. So that would be my pragmatic answer, but I'm not sure that it entirely helps you, because it is difficult when you teach something that you don't personally agree is correct, or where you've got evidence it isn't. The rumor that it will be a colder winter due to the rain this summer. Yeah, it's largely a rumor. I haven't seen the most recent South African Weather Service seasonal forecasts. They should be putting out their updated ones probably at the beginning of March for this winter. It could be slightly cooler because of La Nina conditions, but again, in South Africa, we don't have a direct translation of La Nina. It's very much as that's translated to us via thermohaline circulation. We would have to look at what's happening with our Indian Ocean dipole and the southern annular mode far more than that. Just the fact that there is rain in summer doesn't mean that it would be colder, but I think that the mechanism to explain that would be that more rain in summer over the interior is common for La Ninas, and in La Ninas we might have cooler conditions than we would have in an El Nino. But that's as close as I can get to that one. We'd really need to look at the seasonal forecast there. And I think, again, it's important to recognize that the longer we have hard lockdowns, particularly in places such as the UK and the US, there is an impact on our climate. It's not completely negligible, and that will start to have an impact in terms of what we experience. But we're not about to go into a snowy winter. Over here, in the US, certainly at the moment, New York, I think, had snow again yesterday. They're definitely having these very typical cold conditions, which again is not directly La Nina because we're talking about the Atlantic side, but we're seeing sort of the global representations then in terms of what's happening to the Gulf Stream. And yes, the willy willies. I agree.
Yeah, I think that's every teacher's pet hate, but anyway. That's awesome. Yeah. Thank you. Just to draw everyone's attention to the link in the chat, please, for the quiz. Please take part. Yay. Everyone can take part. It doesn't matter if you're a SAGTA member or not. You might just be the lucky one. If you get full marks, we'll put you in a draw, and Pam will decide who gets the book prize, which is so exciting. So let's see. It's not looking very good at this stage for the people who have entered already, but please answer those questions. Right. Are there any more questions for Jennifer? Not.
Jennifer, there is one there. The USA current weather due to the polar vortex.
Yeah. So the polar vortex is always there. So it's much weaker in summer months. It's much stronger in winter months. And where our jet stream starts to move slightly further north, you're going to have a greater impact of the polar vortex. And as our Gulf Stream weakens, which it does seasonally and it does interannually, that can also allow for an expansion of the influence of the polar vortex. And it also counteracts, if you have a strong Gulf Stream, you've got a lot of warm water moving across from Florida, that would counteract the effect of the polar vortex. But yes, when you see the very, very strong snowstorms in the US, and again, we're seeing it in Europe at the moment, that is the influence of the polar vortex.
Right. Thank you, Jennifer. And we've managed to finish within an hour, which is fantastic. That was fascinating. I think everyone is absolutely thrilled with what you've shared with us today. Thank you so much. I hope we get to hear some more from you in the future.
Yeah, absolutely. As I say, it's really, really wonderful speaking to all of you. And as I get closer to having this book out, if you are interested in a talk on tourism and climate change, it brings together two very different parts of geography, which I think, particularly at school level, we seldom bring together. I'd be very happy to do so. I'm on sabbatical from May until September, so towards the end of September, that would be wrapped up, and I'd be very happy to do so. But thank you all for your engagement. It's always wonderful.
Thank you. Yes, no, we'll definitely get hold of you after your sabbatical. Thank you. Right, goodbye, everyone. Have a great afternoon. Thank you, Bridget. Yes, join SAGTA. Bye.